Hey folks, in lesson 11 we're going to use the tools that we've already developed to demonstrate the development of the equation of motion, constraint force, and some other things about this particular problem using an accelerated box. And then at the end of the derivation we're going to have just a quick discussion on the idea of Newtonian relativity. This is something we've talked about in class before, but using these tools you can actually demonstrate this and test reference frames to see whether they're inertial or not. So what we have here is a box that's accelerating to the right at an acceleration of a. And then there's a pendulum inside of it that's swinging. And so we want to find both the equation of motion as well as the constraint force. And then we want to find the equilibrium angle of that simple pendulum if it's actually swinging in the accelerating box. So, like all problems, we want to start out making a model, which is given here, of the box. It's accelerating to the right, we have our gravity vector, and we actually have all of our coordinates already, because we have x, which is giving us our position relative to O, which is in the inertial reference frame, or fixed, and then theta, which is our second coordinate. And so, like in all problems, we start out, or our next step rather, is to define these reference frames. So we need to define two reference frames for this, and we know that's true because we need an inertial reference frame. And we've also said in class that the rule of thumb is that for every rotational degree of freedom, we need a reference frame. This is a 2-degree of freedom problem because we have a translational degree of freedom and a rotational degree of freedom. But because there's only one rotational degree of freedom, we need to have one more reference frame, not two, than the inertial frame. So let's define those. So for our inertial reference frame, let's use point O as our origin. We'll have an axis going down and an axis to the right. And so our inertial reference frame, we use point O as the origin, we use E1, E2, and E3. So let's put those vectors on there. Let's have E1 going down. We'll have E2 to the right, and then 1 cross 2 gives us a vector that's pointing out of the plane, or out of the page. And so let's define each one of those explicitly. So E1 is defined as a vector pointing along the line O prime P when theta is equal to 0. Then E3 is out of the plane of motion, and then E2 is simply going to be E3 crossed with E1. So there's our geometric definition of our reference frame I. Right, so then we add one more reference frame. And so to this, remember, we're adding this reference frame because there's a rotational degree of freedom, so let's add a rotational reference frame. So let's make a reference frame in which we have an axis along the pendulum and then an axis that's perpendicular to the pendulum. And so this will be reference frame B. And reference frame B, we're using the origin of O prime, and then we use the vectors B1, B2, and B3. Let's draw our vectors on here. Let's have B1, and we'll have B2. And then 1 cross 2 gives us 3, which means that we have a vector B3 that's pointing out of the plane. And so we define these as B1, and this will be along O prime P, and it's always along O prime P. B2, or rather B3 rather, B3, let's put that in the same direction as E3, That never changes. They're both pointing out of the page. And then B2 simply being B3 cross with B1. Now we've used this before, and we can also call these, if you'd like, you can call this ER, E theta, and EZ. So this is a polar frame, just like ER, E theta, EZ, except we just decided to call it B's. It really doesn't matter. Use what's comfortable for you. So now we have these two reference frames, and they're rotated with respect to each other by the angle theta. So that means that we need to be able to transform between these reference frames. So let's define these transformations. So to do this, we need to draw our unit vectors. So for a transformation, let's draw these vectors. We have E1 pointing down, we have E2 pointing to the right, we have B2, or rather B1, and then B2, and those vectors are rotated by an angle theta. So if we express B1 in the E1, E2 basis, then B1 is going to be equal to cosine theta E1 plus sine theta E2, and then B2 is equal to minus sine theta E1 plus cosine theta E2. Right? And so that gives us a table, a transformation table, in which we're transforming our B's using the E sub 1, E sub 2 basis, and we get this table where we have cosine theta, sine theta, minus sine theta, cosine theta. Now we can transform any vector from our inertial basis to our basis in the B reference frame, or vice versa using our transformation table. Now there's one other thing that we need, since we introduced taking the time derivatives of unit vectors, but we also need to define the angular velocity of reference frame B as observed in reference frame I. And so we called that omega B as observed in I using our superscripts. And this rotation is through a rotation of theta, okay, and it's theta in the B3 or E3 direction. Okay, either one of those are going to work, but like we said in class and also in recitation, is that this is going to be the easiest way to do this is theta dot, and then use B3, because oftentimes that's what we're using when we take this cross product, is we're actually using the basis in a reference frame that's not inertial. Our next step in the process is to find our kinematics. And so specifically, remember, for our kinematics, we need to find the acceleration of point P. So find the acceleration of point P, which is where our mass is located, as observed in the inertial reference frame, so we can use Newton's second law. So let's go back and look at our system. And so point P is at the end of the pendulum, that's our mass. And so our position vector is going to be made up of x in the E sub 2 direction, and then L, which is a fixed distance, in the B sub 1 direction. So let's write that out. R of P with respect to an inertially fixed point is equal to x along the E sub 2 direction plus the scalar L in the B sub 1 direction. So let's find our velocity, and it's our inertial velocity. So this is d dt as observed in reference frame I of our position vector. This is equal to x dot, because remember this is a coordinate that can move, x dot in the E2 direction plus L, using the chain rule, our time derivative of the unit vector B sub 1 as observed in the inertial reference frame. So let's work on that term. The time derivative, as observed in the inertial reference frame of B sub 1 is equal to omega of reference frame B observed in the inertial reference frame crossed with that vector B sub 1. So let's transport this in. So it's theta dot B sub 3 cross with B sub 1, and so we get from this theta dot B sub 2. Substitute this in, so we get the velocity of point P as observed in the inertial reference frame is equal to x dot in the E2 direction plus L theta dot in the B2 direction. So let's make sure that this expression makes sense. So here we've got an x dot in the E2 direction, and so we can see that that x dot is an expression of the velocity of point O prime with respect to O. And so you can even rewrite this as v sub p as observed in the inertial frame I is the same thing as v of O prime with respect to point O in the inertial frame. Okay, and so that's our first part, x dot in the E2 direction. And then notice the second part, we get L theta dot in the B2 direction. So it's L theta dot here in the B2 direction, and we've seen this before when we were working in the polar frame. And so this is the velocity of that point P, okay, with respect to O prime. And so if we write this out, it's the velocity of point P with respect to O prime. And so you can even take these guys and add them up. You can solve for them separately. The velocity of P with respect to O prime in the inertial reference frame. We've seen that before in the simple pendulum, plus this now linear velocity. You just add them up because they're each vectors. That gives us this final vector of the velocity of point P with respect to I. So moving on to acceleration, the acceleration of point P with respect to O in the inertial reference frame is going to be the time derivative in the inertial reference frame of the velocity of point P with respect to O in the inertial reference frame. And so this will be equal to, now that we have, this is the expression we're differentiating, so this is equal to x double dot in the E2 direction plus L theta double dot in the B2 direction plus L theta dot multiplied times the time derivative in the inertial reference frame of the unit vector B2. Let's solve for this time derivative. So time derivative of the unit vector B sub 2 is equal to, it's omega of B observed in the inertial reference frame cross with B sub 2. So this is theta dot B3 cross with B2, and we get from this a negative theta dot in the B1 direction. So we substitute all this in, we get the acceleration of P with respect to point O in the inertial reference frame is equal to x double dot in the E2 direction minus L theta dot squared in the B1 direction plus L theta double dot in the B2 direction. Okay, so there's our general expression. We substitute in, we know that x double dot is equal to a, the acceleration, that's what's given in the problem. And so our final expression here is that our acceleration of point P in the inertial reference frame is equal to a in the E2 direction minus L theta dot squared in the B1 direction plus L theta double dot in the B2 direction. Once again, let's look at our terms, and we have the acceleration of the box to the right in the E2 direction, and we're adding to that the acceleration of the pendulum. And so we can write that as the acceleration of point O prime with respect to O plus the acceleration of point P with respect to O prime, both of these observed in the inertial reference frame, This gives us our acceleration of point P observed in the inertial reference frame. And so this should make sense because we've got our linear acceleration, and then in our pendulum we have our centripetal acceleration, so it's pointed in the negative b1 direction, and then we have our tangential acceleration of that pendulum, simple pendulum, in the b2 direction. Alright, let's create a free body diagram so we can apply Newton's second law. And our free body diagram shows us with our mass. We have gravity that's acting on the mass, and that's in the E1 direction. And then we also have our constraint force, and for our constraint force, we'll say that this is happening in the negative, so it's negative n, there's a magnitude in the B1 direction. So it's constraint force in the negative B1 direction, and so our forces on the particle, because we're going to apply Newton's second law, Fp is equal to m AP in the inertial reference frame. Forces on the particle are equal to negative n in the B1 direction plus mg in the E1 direction. And so let's apply Newton's second law. And when we apply Newton's second law, we take our force, put it on the left side, so negative n in the B1 direction plus mg in the E1 direction is equal to our mass multiplied times our acceleration observed in the inertial reference frame, which is a E2 minus L theta dot squared in the B1 direction plus L theta double dot in the B2 direction. And so we need to convert into the same basis so we can continue to get our scalar equations. You can see here that we've got B1s, a B1, a B2, we get an E2 and an E1. Now, here let's convert from E1 into E2, and so to make that conversion we need to go back to our transformation tables. Okay. And so to convert from E1 into B1 and B2, we get E1 is equal to cosine theta multiplied times B1 minus sine theta in the B2 direction. So let's write that out. E1 is equal to cosine theta in the B1 direction minus sine theta in the B2 direction, and E2 is equal to sine theta in the B1 direction plus cosine theta in the B2 direction. Okay, let's substitute all that in, and when we do, we get minus n in the B1 direction plus mg multiplied times quantity cosine theta B1 minus sine theta B2 is equal to ma multiplied times the quantity sine theta B1 plus cosine theta B2, then tack on the rest, minus ml theta dot squared in the B1 direction plus ml theta double dot in the B2 direction. Alright, so we've got one vector equation, and so this vector equation in the B1, B2 direction, we can equate our coefficients to give us two scalar equations. And for this in the B1 direction, we'll get minus n plus mg cosine theta is equal to ma sine theta minus ml theta dot squared. And in the B2 direction, our coefficients are minus mg sine theta equal to ma cosine theta plus ml theta double dot. And so we see here that we've got two equations. Our top equation gives us our constraint. This is our constraint equation, in which we can rearrange for this and solve for our constraint force. We get n is equal to m g cosine theta minus a sine theta plus L theta dot squared. And then we also have an equation of motion. And we recognize the equation of motion because it's in second order form. And so our equation of motion for this system is theta double dot is equal to minus g over L sine theta minus a over L cosine theta. And so with these two equations, we've got the information of everything that we need to know about how that particle moves that's on the end of the pendulum, as well as what force is going to be in that string or in that massless rod in which it's attached to. Now take a look at the equation of motion here. We've got theta double dot is equal to minus g over L sine theta minus a over L cosine theta. So what you see here is that we have the simple pendulum, the equation for the simple pendulum, buried within this larger equation of this simple pendulum in an accelerated box. And so what we see here is that how the pendulum is affected by the motion of the box is that it's going to swing normally with its normal harmonic motion, but then it's going to end up having some sort of offset. So if it's a constant acceleration, there's going to be an offset of this a over L cosine theta. So what we want to do now, the third part of this problem, is solve for what would be the equilibrium point, or the offset, if there were no motion, if there were no actual simple harmonic motion going on, but only just the pendulum itself being displaced due to the acceleration. So what we're actually looking for is an equilibrium point. And let's do that with our simple pendulum first, just so we can get a better handle on this. The equations of motion for our simple pendulum are theta dot is equal to negative g over L sine theta. And so if we want to find the equilibrium point, then we set theta double dot equal to 0 and theta dot equal to 0, and then we solve for our position at that time. Now in this equation of motion, we see that there is no theta dot term, so we can set our theta double dot equal to 0. We'll set this equal to g over L, and then sine theta, we'll call that theta equilibrium. And so when we solve for this, the only way that we can get 0 is for our equilibrium theta to be 0 as well. And this should make sense to you for our simple pendulum, because there's the equilibrium point. The equilibrium point is when theta is equal to 0. That's when we're not going to have any acceleration at all in the rotational direction. So let's look at the equation of motion for this pendulum in an accelerated box. And we got theta double dot is equal to negative g over L sine theta, and then that was minus a over L cosine theta. Okay? So we're going to do the same thing. We're going to set theta double dot equal to 0, theta dot equal to 0, and then solve for the theta that solves for this, that satisfies that condition. And so we get 0 is equal to negative g over L. This is sine theta equilibrium minus a over L cosine theta equilibrium. Alright, let's move our sine theta term onto the other side and divide through by cosine. So sine theta equilibrium, g over L sine theta equilibrium, is equal to negative a over L cosine theta equilibrium. Divide through, and we'll get tangent theta equilibrium. Multiply both sides by L over G, and then we'll get tangent theta equilibrium is equal to negative A over G. And so solve for theta equilibrium gives us our arc tangent of negative A over G. And then because tangent is an odd function, theta equilibrium is equal to negative, we can just pull our negative sign out, tangent of A over G. And so what this is saying here is that if in our box we have our pendulum and our box is accelerating at an acceleration of a, then what we have is our pendulum is going to, so our pendulum is going to be at an angle of our negative inverse tangent of a over g. And so if we're accelerating to the right, then just our intuition should tell us that our pendulum should be hanging to the left, okay, because we're accelerating. And so recall that we had defined our theta as positive to the right, so that means this magnitude that it's being pushed to the left is going to be this arctangent of a over g. All right, so this is just like it's the fuzzy dice problem. It's if you're in your 57 Chevy and you've got your fuzzy dice hanging from your rear view mirror and you are pulled up at a stoplight and you accelerate out of there, the fuzzy dice are going to tilt back to you. They're going to be like a simple pendulum and tilt back to you until you get to a constant speed. And then what happens at the constant speed is that they relax, they then become vertical again, okay? And then you keep on going along your way. So this equilibrium is present when there's a constant acceleration. And so that's what we see here, and that's how you could calculate that angle. So now let's take a closer look at this problem and put this into the context of multiple reference frames. Let's add a reference frame and to get some more intuition about this idea of Newtonian relativity. So here are the reference frames that we started with. We got our inertial reference frame, and then we called this reference frame B, which was attached to the pendulum itself. And let's add a reference frame, and let's add a reference frame that we'll call reference frame A, which is essentially in line with the inertial reference frame, but because it's attached to the box, it's moving to the right. All right, so let's define that in detail, where we have reference frame A has an origin at O prime. O prime is fixed within reference frame A. It's in the box, and then we'll give it vectors A1, A2, and A3. And A1 being defined as along OP when theta is equal to 0. A3 defined as the same as E3, and then A2 being E3 crossed with E1. So let's put these up on our plot. So we have A1, and then A2 and E2 are in the same direction, and then B3 and A3 are also in the same direction. Okay? And so the only difference between these reference frames, between reference frame I, which we said I is equal to O, and that's E1, E2, and E3, the only difference between these are the origin. We have an origin at point O for reference frame I, and an origin of point O prime on reference frame A. And so that allows us to now have, because O prime isn't fixed within the inertial reference frame, it's moving with respect to the inertial reference frame, and it can accelerate within that reference frame. Alright, so let's get an idea of what each of the kinematics looks like within each of these reference frames. So for reference frame I, we said that we started out with R, P with respect to O. We chose P as with respect to O because O is fixed within the reference frame. So that's X in the E2 direction plus L in the B1 direction. And then when we find our velocity of point P as observed in the inertial reference frame, we get simply X dot E2 plus L theta dot B2. And then our acceleration as observed in the inertial reference frame of point P is X double dot E2 minus L theta dot squared B1 plus L theta double dot B2. Alright, reference frame I in reference frame A, if we make these same calculations, it's r and it's p with respect to O prime, because O prime is fixed within reference frame A, and that's L in the B1 direction. Okay, so you can see that here. It's the length L in the B1 direction. That's the only part of that we take in reference frame A. And then our velocity of point P observed in the A reference frame is equal to L theta dot B2, and then our acceleration of point P as observed in the reference frame A is equal to minus L theta dot squared in the B1 direction plus L theta double dot in the B2 direction. Alright, finally let's look at reference frame B. We're going to observe the kinematics in reference frame B. And so our position vector of P with respect to O prime is equal to the same as reference frame A. It's going to be L in the B1 direction, and that's because these two reference frames share an origin. Okay, I should point that out. These share an origin. Okay, and then the velocity of point P as observed in reference frame B is equal to 0. We saw this with the path frame the other day, because when you're observing this point P in reference frame B, it's a fixed distance L. And so in reference frame B, if we're looking at this from that perspective, it doesn't move. So if it doesn't move, then that means that the acceleration of point P in reference frame B is also 0. Now remember that we only care about our acceleration in really any of these situations. Okay, currently, in the next chapter we'll care about velocity, but right now we only care about acceleration. And so for our acceleration, we only care about acceleration because of F equals ma. And so let's make a comparison between each of these using our inertial reference frame as our gold standard. This is what we would need to be like in order to use one of these other frames of reference. So let's use the easy one. So if we observe the acceleration from the standpoint or from the point of view of reference frame B, we see that acceleration of point P within reference frame B is always going to be 0 in this situation. And so what we see here is that acceleration of point P as observed in the B reference frame can never be similar to the acceleration of point B as observed in the inertial reference frame, except for in the trivial case where all these terms in the inertial reference frame are 0. X double dot is 0, B1, B2, all these terms are 0, and that's really a trivial case, so we don't care about that. So that just means that we can never observe or use our observations in the B reference frame and apply that to Newton's second law. But let's take a closer look at reference frame A. And in reference frame A, you can see we've got terms that look the same, and those are our B1, B2 terms in both sides. The only difference, though, is this term here. And this term here, this x double dot in the E2 direction, this is a term of linear acceleration. Remember, this is the linear component, it's that coordinate, it's not our rotational component. So what we see is that the acceleration of P, when observed in the A reference frame, can be equal to the acceleration of point P as observed in the inertial reference frame, only if x double dot is equal to 0. Or in the way that we structured this problem, when A is equal to 0, our acceleration is equal to 0. And so this tells us something really important. It tells us that, and we've said this multiple times, that although frame A is not fixed to the stars or fixed in absolute space, like what is required in Newton's second law, when it's moving at a constant velocity, or in other words, x double dot is equal to 0, with respect to the inertial reference frame, you can use observations in the reference frame A to apply to Newton's second law. And so therefore, when this occurs, reference frame A is an inertial reference frame. So let me say that again. When reference frame A is moving at a constant velocity, or in other words, the acceleration of reference frame A is equal to 0, okay, that relative acceleration, then you can use its observations just as if it's an inertial reference frame. And so this is the idea of Newtonian relativity, which is saying that every non-rotating frame moving at a constant velocity in absolute space is an inertial frame. And so if we go back to reference frame B, it's automatically out because, as you see here, it is a rotating frame. Okay, it's rotating relative to the inertial reference frame. This reference frame A is a non-rotating frame, and if A is equal to 0, if the acceleration of that frame is equal to 0, then you can use that as an inertial reference frame. And that's why, if we go back to our fuzzy dice problem, that's why whenever you're accelerating, you see the pendulum, or you see your fuzzy dice tip back toward you. It's going to rotate toward you because you're now observing that from a non-inertial reference frame because acceleration is not equal to 0. But once you get to that constant speed, the fuzzy dice tip back, it's looking straight down, and then you're back to this situation in which your equilibrium point, at least with this pendulum, is theta equals 0, and then you're now making your observations once again from an inertial point of view. All right, I'll see you in class tomorrow.